Okay, shall we begin? Pointer's missing. Pointer. If you're a pointer, where'd you be? You would be. I guess I'm doing this. Oh, here we go, pointer. Okay, let's mess with the light, shall we? Is that better? So, sorry I'm late, but today will be yet another really fast lecture, because everyone loves 20-minute lectures, right? No? Oh, sadness in the face? All right. You look disappointed? I can talk longer if you like. Any questions from last class? Chi-squared is pretty straightforward. So to review the tests that we've done thus far this semester, we've done the z-score test, we've done t-tests, we've done correlations, we've done ANOVA, and now we've done chi-square. I missed one? You have a couple more to go, and then you'll have the holy set of tools for fighting all statistical evils at the most basic level anyway, well beyond what many introductory courses touch on, by the way. In fact, many courses will just focus on the things dealing with the normal distribution. With chi-square, we're not dealing with that anymore. We're dealing with different kinds of distributions. So let us continue on slightly more with the chi-square. Just a couple more nuances to introduce today. And oh, we're live. Look at that. The video is actually working today. So let me just move the camera so you can see the screen, which nothing is on now. That's good. All right. So remember, the null hypothesis for the chi-square was that the two variables we're trying to compare are independent. They're not related. Nothing's going on. But we introduced that word independent now. Previously, that wasn't part of the null hypothesis statement, but now think about it more and more. And it's essentially saying that the proportions under each category are going to be the same. And of course, the alternative is they're not the same. They are related. So the values of one category disproportionately affect the values in another category. So to do the chi-square, we have to make that contingency table again. We've only done so far an example with a 2x2 because that's the easiest. Today we'll try a larger example. And we have the observed values, which is what? What's the observed values? What do I mean by observed values? No one meets my eyes, I glance across the room. No, yes. But sorry, there it is, not a trick question. It's the data. Okay? So, and it's a terminology that will carry forward through all of science. Your observations are the data. Okay, and then we compute the expected values, and the expectations are based upon if the numbers were to splay in a universe in which there was no relationship between the variables. In other words, if they were to be randomly allocated to each of the cells, what would we expect to see? And then we compute the degrees of freedom. Remember the formula for that? It's the rows minus 1 times the columns minus 1. Very simple with input numbers. So the assumptions again. This is important because the assumptions will tell us whether or not we can apply the chi-square, and if not, depending upon which assumption is violated, what modifications we need to do. So this random selection, each observation is independent. What does that mean? It means that one observation doesn't affect the next one. So if I measure this on you this time, am I going to measure you again to see if you got better? That's a repeated measure. Those are related constructs, related observations. So the chi-square assumes that they're not related. We have something else to deal with that situation. In fact, we are related. We'll see that in a second. We have this assumption that each cell of the expected frequency is greater than 0. I will add a caveat to that, which we'll see later today, which if it's less than 5, we have to do something as well. But 0 is our hard cutoff. And each cell must have an observed frequency greater than 5. Frequency, if you're not used to the word, the way this word is being used here, it's just the number in the cell. That's what frequency means. Remember that from the first week, the frequency distributions, that's just the count. Right? So the critical one that comes up all the time is that the observed number in each cell must be 5 or greater. And if not, then we have to do another test. Do you remember the name of that test? The test that we do if we don't have at least 5 in each cell? No, it's, yes, back there? Fisher's exact test. Some people just call it the exact test. Okay. And mentioned as well that there are variants of the chi-square, not really variants, but replacements in case the data is not nominal. If is ordinal, we have two other options. Do you remember those options? Yes. The Man-EU test, exactly. Kruskal-Wallis test. I know, it's like a memorization class for bizarre European names, right? But on the plus side, I'm not asking you to learn how to do those tests. Just remember when you apply. So, as the slide says, if the observation is less than 5, we do Fisher's test. Now, if the expected value is less than 5, I said the hard cutoff was 0, and that's true, you can't do anything with 0. If the expected values are less than 5 in any of the cells, we should apply something called the Yates continuity correction. We won't be doing that in this class. Good for you, right? One less thing to learn how to do, but know it exists and know when we would apply it in a real-life scenario. So what it does, the Yates continuity correction actually reduces the chi-square number by a smidgen and makes our estimate more conservative. And by more conservative, what we're saying is it makes it less likely that we'll find significance. And remember, this is the formula for chi-square. The Yates continuity correction, can I stand, I'm not blocking the path, is right here. Is that 0.5. You take away half of every one of these computations, named after Frank Yates, who did this in the 30s. Again, I don't need you to do this. Just be aware of what it is and when we would use it. I don't need you to know Frank Yates is 1934. It's called the Yates continuity correction, and it's applied when the expected values are less than 5. And maybe that it's a conservative estimate. So that's the chi-square. Now, the Yates correction only applies to 2x2 and 2x1 tables. So if I'm being an asshole, as I often am, I may ask a question like, hey, here's some data, and it's a 4x6 table, and there's a couple of situations where the cells are less than 5. And I'll say, is this appropriate for Yates continuity correction? Well, yes, of course, but no, because it's not a 2x2 table. That's the kind of asshole thing I would do, because I'm that guy. Right. Right, here we go. Here is an example. Warning labels and seatbelt laws have resulted from the use of this test. And that's true. I mean, you're too young to remember, but I was around when Ontario changed their seatbelt laws. Suddenly, it was compulsory to wear a seatbelt in cars. You can't believe that it ever wasn't, right? But I grew up when it wasn't. Very rare for people to use seatbelts. And it was a hard sell by the Ministry of Transportation to actually get people to wear seatbelts back in the 70s. And a lot of the data coming out of that time had to do with cross-tabulations. Right? So can you imagine the research question that was asked that allowed them to use a chi-square to answer the question, is there an association between seatbelt laws and safety? There are many right answers here, but can you imagine? I'll let you start thinking like researchers now.